So here's a summary of what we've done so far. So we started with our basic model. So let's just remind you of what it looked like. It looks like this. The derivative of the voltage, I guess we can write it like this. This is, I think we wrote it like this on the last, on homework 2, I think it was. Let's get my email out of here. It's all over the place. So we can write it like this. And you'll remember this from, I think, homework 2. So this thing can be solved by hand for, I don't want to say most, that's a, so let's say it this way, provided I guess the better way to say this is this can be solved by hand for, what's happening, I'm losing. Can be solved by hand for some inputs I of t. So the way for you to think about what this equation models is, imagine we have a cell in some experiment laboratory, and we hook some apparatus up to it, these clamps, if you will, and what we do is we input charge into the cell, and then we study what the cell does. And we talked about how what we're thinking about is the potential difference between the voltage inside and outside of the cell. And then we're also incorporating this idea that chloride somehow, these ions in and out of the cell sort of affect the behavior. And so again, this equation has a solution that is a good model. It's not perfect, it's not excellent, but if we go and do the experiments and then we take our data and we compare our data with the solution to this equation, we seem to get, in most cases, good results. It's a good model. So that's the good news. It's good in some cases, but it's not always great. And so we should also note that for many inputs, we can't obtain an exact solution. But we can use numerical methods to approximate the solution. And this is what happened is when we got to this point, we said, okay, there's a couple things that we can do. If you look back at the notes, the key feature is that there's this integral that pops up and it was like e raised to the power, and it was times I. And if I is simple enough, then we can integrate that. But if it's not, then we can't integrate it. And at that point, that means we'd have to either A, use things like numeric integrators like Simpson's method or the trapezoid method, or we solve the differential equation using a numerical means like Euler's method. So when we got to this point, this brought us to so at this point, we have to learn how to either write our own Euler scheme, or we can learn how to use ones that are built into software like Mathematica, or we've used Octave here. The reason I chose Octave is because it's free. And it's also good practice. It's a good skill for you as students to learn how to write your own code. And so I took some time, I gave you some code. I hope that you try and work on that. And again, I emphasized this last class on Monday. It's very difficult for us to master this portion of the course in this virtual setting. It would be much more efficient for you and for me if we were sitting in a classroom right now and everybody had a computer in front of them, and we can walk around and we can look at your code and we can help you fix it and help you get the pictures to come out correctly. But unfortunately, we can't do that. So we have to make the best of this. And that means if you want to get something out of this course, it's going to require a lot of effort on you outside of being here. Now, I'm happy, of course, to meet with you at any time and discuss things virtually, but you guys have to let me know what you're struggling with and the questions that you might have. So again, you got to think of this is especially because we're virtual. What you're going to get out of this course is so much dependent on what you're putting into it. We're just so limited on, you know, the things that we can do when we're not face to face. Okay, so so what is Euler's method? Euler's method is a very basic, and I mean that in the most English sense of the word, it's simple, is a very basic tool for solving differential equations on a computer. And let me remind you, we're saying solving, but what we're doing is it's much deeper than that. We're not solving it in the sense that we're getting the answer. What we're doing is we are using some deep theorems, and deep theorems tell us that the solution exists and is unique. And that means that when we use an Euler scheme, it is approximating the solution that's out there. So that's kind of hard when we're in the position that you guys are in right now. You're saying, how you just told us we can't find it exactly, but now you're telling us the theorem says it exists. Well, that's true, but think of it even in an algebraic term. You know, if I said to you, solve this equation, what are you going to tell me? You're going to tell me that it's a square root of 2. Right? That square root of 2 is a symbol that human beings invented for the solution to that equation. Because the solution to that equation is an irrational number that you can't find exactly. It goes on forever and ever and ever. You can't write down the exact value of the square root of 2. The best thing you can do is invent a symbol for it. However, long ago, we realized that we can't invent this symbol because we all understand that that irrational number, the square root of 2, we can approximate it to any degree of accuracy we want. And so then, being that we don't want to write, 2.1 blah, 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 excuse me, we invent this symbol, just like we invent pi and e, and. So with differential equations, it's very much the same. We know the solution's out there. We just can't write it in terms of the elementary functions that we're used to working with. So what we do is we use a computer to approximate that scary solution to any degree of accuracy we want. So I hope this is clear. I don't know if it is, and I feel I often, it's hard for me to take my brain back to that time when I was sitting in the same position that you were sitting, and you're very much like, what is happening, right? But you got to really, sometimes these are things that you got to think about, and you got to think about more and more. Because one of the things that you'll learn when you start taking higher level mathematics and you start getting into courses in engineering and physics, what we end up doing is we end up approximating things that we can't actually determine precisely. But luckily, the mathematical theory, the big theorems tell us that even though we can't calculate you exactly, we can approximate you to any degree of accuracy we want. So you need to think about that. Okay, so let's delete this because it seems out of place. Now, there are much more sophisticated numerical tools. So let's call them these ODEs. So let's just list a couple of them. So what you can do, and I would encourage that you Google this and read about it. It's not hard to learn. Probably the most, I mean, look, I'm not going to even write it. You can learn about this if you Google it. So one of the things we do, for a good analogy, for a good theme, think about when we learned about numerical integration in Calc 2. We start with these Riemann sums that are rectangles, and then after we figure that out, we're like, well, we can get rid of all that air if we use trapezoids instead of rectangles. And then Simpson's rule says, well, why don't we approximate curves with simpler curves? And that's where Simpson's rule comes in. And so we can use the same idea when we're trying to solve a differential equation. And so perhaps the most common and widely used ones are what are called the Runge-Kutta methods. So I don't want to go into this too much, but you should read about it if you want to learn. And some of you may have already learned this in a differential equations class. So if you're interested in learning about this, I say Google them. And there's lots of very easy to learn resources about it. And essentially what they are is they're just more sophisticated versions of Euler's method where you try to eliminate errors so you don't have to do as many calculations on the computer. Okay. So Octave, which is nice, you don't even have to program it. Now you could for practice. It actually has this built in. And what it's called is ODE 45. And the 4 and 5 have to do with one of the particular Runge-Kuttas is, so Runge-Kutta is a, notice I use the plural methods. There's many different ways you can do it. And One of them, the more common ones that sort of converges to the precise solution rapidly, is ODE 45. So you can Google that term and you can read about it. It's a MATLAB thing, so it works on Octave. Perhaps one of the things that you might want to Google, suppose you want to learn about the Runge-Kutta or the ODE 45. Anytime you do a Google search, type that in, and then right after it, put PDF. And then you're more likely to come across hits that are from classes in these courses. And there'll be examples, and it's much easier to read that than perhaps the Wikipedia page or the official page from MATLAB. So, you know, I would encourage, you know, that you Google these things. So let me write that down just to remind you. So if you put the PDF at the end, you're more likely to come across materials from a class, and usually that's a little easier to learn from. But you might even go to YouTube and watch videos. I'm sure there's videos of people showing you how to do this stuff. And of course, I'm going to give you code, and we'll talk about it too. Because the nice thing about using ODE 45 is that you don't have to do as much work as when you're using Euler, and it's more effective, it's more efficient. Does anybody have a question, comment right now? Comments, concerns? All right. Okay, so again, let's keep with what we're at. So we then get to the famous model and that is the Hodgkins-Huxley equations. So I'm not going to write them down again because it's cumbersome, but the important thing to remember is this is a system of 4 nonlinear differential equations. So let me point this out again. Now again, when I say solving, I mean on a computer. When we solve this system, we obtain the more accurate picture of what we call the action potential. So that is, again, what we talked about that before. That is when the electron, a very sort of babyfied way of thinking about this is that you have cells, these neurons and these nerves, and they're all connected. And they send messages to each other. And how they communicate is they communicate through electricity and then also some chemicals, potassium, chloride, sodium. And what happens is as these things communicate in different ways, as they send these signals, the voltage sort of charges up, and then the neuron, what we say, fires or has an action potential. The voltage starts to increase, and then it explodes, and then it drops back down and comes to its resting state, which we talked about in many examples as being like negative 68 millivolts. And so we're trying to capture that image. We want that image. I've showed you it numerous times where it looks like this. Where if you have your voltage, it's just chilling down here, and then it starts increasing, and then it fires up, and then it comes down, and then goes like this. That's what we want to mimic. We want a function whose graph looks like this. So I sent you guys, I think it was last week or something, I posted on Canvas, I posted some readings from a textbook. And I told you, you know, if this were, I mean, this is a math class, so we're sort of doing it from the math perspective. But what I sent you is some readings. If you really want to see how these equations are developed, you have to have some knowledge of some basic physics, and also some chemistry, some biology. And for those of you who have had some of those physics classes, it'll be a little easier to understand. Some of you didn't, and so it's going to be a little more difficult to understand. But it's there for you if you want to learn about it. And for those of you who were in a physics class, even if it were in high school, what we model this behavior of the cell is we model it after like a circuit diagram. So maybe I can pull one up here. So if I switch, let me share to a different page. If I share this, perhaps in physics class, you guys did something like resistors and capacitors, and you drew elementary circuit diagrams. This is how we're getting these equations, and then we're using things like Ohm's law in some fundamental and basic things that we learn about in physics. And when we use these laws, what happens is you arrive at differential equations. And again, I don't want to go too much into that. Now, if you ever wanted to talk about it, I'd be happy to meet and discuss it with you. But I don't know if going through all that in this class is the best way of doing it, because this is a math class. Does anybody have a question about this? So if you Google LRC circuit, let's see if we can get. See, when I Google this, you see these pictures that we want to get, and very fun. Okay, does anybody have a question about this? Comments, concerns? Going once, going twice. Okay. So I shared with you, and perhaps I'll share it again. Let me pull it up. I was just playing around with it this morning, actually. So hopefully you're seeing my octave. And what you'll notice is I was able to obtain the picture in one scenario that's much more realistic than what we originally got with our first model. However, what you'll see is there's a lot more happening in my workspace for me to get this picture. I have to tell Octave what everything means, all these functions. So right up here, and like I said, I'll share this with you. Up here, I'm setting all my constants, my capacitance of sodium and all that stuff. And now I have to define all these functions. And by the way, you'll notice I'm doing it differently in here. I'm not using that inline. I'm using a different thing, but it's very much the same. You put this at in front of v, and that's the variable. So this is another way to define functions. And then the way I'm solving it here, and by the way, this is going to be completely overwhelming, and so don't get overwhelmed right now. The way I'm solving it is I'm not using Euler. I'm using, if you look over here, I'm using ODE 45. So this is sort of what you're, as I said, I gave you, the last assignment was for you to learn how to do Euler's scheme for 2 equations. And if you wanted to use Euler you could do it with this, but a more efficient way is to use ODE 45. And so that you should think of that as your goal. You should try to get that. And see if you can get the picture. Does anybody have a comment or a question? Going once. So there's a couple things, I told you guys I was going to have, a couple, projects. So if you look at what we've done already, where'd it go? Where did it go? Where did it go? Oh, I just lost it. So project 1, and so the next thing, I told you I wanted you to have 3 projects because it's important that at the end of this you have something to, your evidence, that you sort of have an idea of how to do some higher level stuff, like one of which is getting the computer to solve these equations. Questions, comments? Maybe you guys, Jingzi and Zacian, you guys, have you guys had physics 2 yet? Yeah, I think so.
Yes.
Yeah, so you mean there's no doubt you've done electric circuits before, right?
Yep.
So that might be something worth trying for you guys, just to see if you can derive the equations using things like Ohm's law and, things like flux and what's called the Nernst potential. Again, I don't know for sure how much of that you guys would have went in. It just depends on who teaches the class. But I know when I was a student in physics 2, we did that stuff. And then you do
yeah, basically.
Yeah, and then we did it very briefly in a differential equations course. We did it very simply. And by the way, I have this other thing. I was perusing the internet for you guys. I'm trying to find accessible material so you guys can learn from. The problem with stuff like this is if it's written from one perspective, it's not, no one's thinking about, so what I mean by that, if it's written from the neuroscience perspective, then there's too much neuroscience and biology and chemistry for most of us who haven't had that stuff yet to follow. And then when it's written from the math perspective, it's often the mathematics is at a higher level that it's more difficult for us to follow. So it's not as easy. Perhaps that means I should write something to make it a little more down to earth, because there's not that much written about this that is accessible for, you know, undergraduate students who don't have, you know, most of this stuff is studied in the graduate level just because of the amount of knowledge that's required if you want to go completely in depth. Of course, that's why we call this an introduction and not something bigger than that. So anyhow, I found some stuff that I'll post along, and maybe you want to read it. That thing I sent last week is rather long. It's like a chapter of a book, but I found another PDF that's just a few pages. It's a little more accessible, and perhaps you guys can learn something from it. So what I want to do now is sort of spell that out for you. So I think this is important for you to think about. So I want you to, there's going to be like, I want you guys to sort of do like a final project. Now, don't get afraid that this has to be some like, you know, insane project, but it has to be something that, hey, Rick, what's happening? I'm well, you?
Hey.
We're just over here learning.
There you go. At least somebody's learning something.
That's right. That's right. So here's a couple things that you might consider for your final project. And I'm going to lead you on these. I'm not going to, you might want to show the derivation of our first model. That's a very simple, you know, LRC circuit. You might want to show the derivation. This is a much more difficult task of Hodgkins-Huxley. And I want you to start thinking about this because we really only have a couple weeks left. And this, you know, if you start thinking about this now, then we can set up some meetings if you need, and you can talk. And again, I'm going to work with you on these things. I'm not going to just say, go do this on your own. I'm going to assist you. So it'll be more like we're working together than anything else. Other thing you might do, you might study our first model with different eyes, different inputs. You know, you might investigate the Hodgkins-Huxley equations with different eyes. So right now you might be thinking, what does he mean by all this? Well, if you're going to do these investigative things, what you would be submitting is you'd be submitting computer code with pictures, and then maybe a little, you know, sort of discussion about it. And if you're doing these derivations, this would be hand calculations. And there's lots of good ideas we can have. And I can even, if you're confused on what to do, I can even give you a problem and walk you through it if it's something. And it doesn't have to be these things. It can be, here's another one that's interesting to think about. can you investigate what we call periodic spiking? So what does that look like? That would be something like where you get your picture, the spike, and then it comes down, and then it spikes, and then, well, that's bad. So this would be, how do you get something like this? Well, you have to have some input that's periodic, and if input's periodic, then you get this behavior of the cell that's also periodic. This is important. We call this a spike train. Can we get this to happen? And so I have a bunch of different mini projects of these things I can walk you through and set you up, but I'm giving you the opportunity, if you'd like, is there something that you are interested in that you want to learn more about? And I'd be happy to work with you guys, again, personally on anything you want. Now, if you're completely lost, then I'll just give you something to do. That's fine. That's completely up to you. And what I'm going to do, no matter what, is obviously help you with the math, and I will also help you with any computing that you want to do. Again, one of the things that we're stuck at here is solving and analyzing are two different things. Solving is going to be mostly done on the computer. If you wanted to do some analyzing of these equations and make certain things, that is more hand calculation. Does anybody have a question or a comment about what I'm saying right now?
So we get to pick our own project, right? In terms of
right? Yeah. So you're going to have.
okay.
I originally said there's going to be 3 projects, but that's not the case. You're going to have 2. The first one I already gave you, if you remember, that was showing how to integrate. Although we should, you know what? We can make a very small second project. You have to solve a couple. Well, we already did that for homework. Well, we'll probably just have 2 projects, and that's about it. Maybe in one more homework assignment, just so we can give you practice, at least one more on learning some new math. Because, you know, if you think about it, you might feel like you haven't learned anything new, but you have. Especially, I mean, when you solve that was it homework 2? Let me double check. I keep misspeaking. So homework 2, yeah. If you work through homework 2, you've done a lot of heavy math. So you're learning stuff. Now homework 3, was the purpose of that was to get you to understand how to use computing tools to help you with math. And again, you're learning important tools that are used in practice by actual mathematicians and scientists. You're not just learning textbook problems, you know. So that's kind of what we wanted, one of the goals from this. And also that you can learn a little bit about the neuroscience aspect of it. Does anybody have, does that answer your question, Jingzi?
Yeah.
Any other questions or comments? Before we do some other, some new math. That we quite didn't, well, I shouldn't say new math. It's not new math. All right, so we're gonna move on. Hi, Edie. Right. Okay, so what's next? What is next. So here's another useful tool that we want to talk about. Well, I guess I should spell correctly. Well, let me write it this way. Another useful tools. So this is poor English. Let me get rid of this. Our next topic of use is Fourier series. So some of you might know what a Fourier series is, some of you might not, and that's okay, but they turn out to be very useful in many applications, and of course here in when we're dealing with anytime we're talking about signals being sent. And as I said before, with the brain, another way to study it is imagine, or not another way, but one method of study is to think about these cells sending signals to each other. And so one way that we learned a while back as humans to analyze signals is to study what's called a Fourier series. So that's where we're at right now. So if I go to the following, and again, if you have a question you need to ask, because I'm not exactly sure how much you guys do or don't know when it comes to this stuff. So if something's confusing, let me know. So it often happens. It's a better way of thinking about it. That a function can be written as a series of sines and cosines. Now, some of you may have seen this before, and where this comes from, maybe you haven't. But you have to trust me that this is something that is of use. So let's sort of, I wrote that in English, but let's think about what it means in terms of mathematics. So here we go. So what we want to do is we want to suppose I have some function f of x, and suppose I can write it like this. So we're going to do some hand waving math right now. So let's suppose we say it is n equals 0 to infinity of some number a sub n times the cosine of nx plus some other number we'll call b sub n right now times the sine of nx. Now, right now you might be saying, where's he getting these from? Stuff like that. And that's okay. If you want, well, again, you could Google this, but just to give you an illustration, for a little historical background, why are these called Fourier series? Well, there's this scientist years ago named Joseph Fourier who was studying heat and other problems. And he had to solve some differential equations. And when you solve these differential equations and these, I guess more technically, they're what are called partial differential equations, he arrived at that you got infinitely many solutions. And so for reasons that if you take differential equations, you learn about, the idea is if you have two solutions, if you add them together, it should be a solution. If you have three and you add them together, it's also a solution. And so the idea is that you get all these solutions, and the word we call them is we call them eigenfunctions, if you've ever heard that word before. And what we realize is, okay, maybe, just maybe, if we add them together and take the series, this infinite series, it's also a solution. And it turns out in many cases it is. And it turns out that what you end up getting for these solutions is you get numbers times cosine plus numbers times sine. So if you're looking for some sort of comparison, think about when you were in Calculus 2, we studied power series. Now, power series were a number times x to a power. So this is a different type of series. So again, what are we trying to do? Well, I'm going to show you a picture. The picture is sort of more illustrative than anything. Here's the idea. Right now you should be seeing a picture. You have four pieces to this picture. You have what we call a square wave. This blue line, imagine this is like a signal, on, off, on, off. And what we're trying to do is we're saying, okay, perhaps I can express this discrete thing, this on, off, perhaps I can approximate it with some continuous and differentiable, nice smooth curve. So here we have these edges, but what we notice is if we add up a bunch of sines and cosines in a creative way, that we get this red curve to mimic the blue lines. And the way to do that is to use this idea that we're talking about. It's to use what's called a Fourier series. So that's sort of what our goal is. Our goal is to sort of figure out how this works and why it works. So what's fascinating is this all came about from studying heat, you know, a couple hundred years ago, and it turns out to have endless applications. I think I mentioned this to some of you, and if you look at the mathematics behind things like foul compression, this stuff pops up. And again, the idea is that sine and cosine have lots of properties that are useful. They're periodic, they have nice behavior, the derivatives are easy to compute, and there's patterns. And so the idea is maybe we can define a function this way. And okay, bye, Ricky, have fun. Okay, have fun. Sorry about that. And not only is this studying this a couple hundred years old, but it led into a whole new branch of math, which we call harmonic analysis. And so there's lots of reasons you would want to study Fourier series, not just because you can use them in studying the neuroscience. Okay, well, go have mommy put them on, please. Okay, so okay, sweet. It's all right. So we have this, let's just assume we have some function that can be defined this way. What properties are we going to have about f? What is a sub n? What is b sub n? So on and so forth. Okay, so I'm lost. I lost my thing. I can't get my pen back. Where is my pen? You guys seeing? Okay, yeah. Okay, so I lost my pen and I can't get it back. It's driving me nuts. Okay, so suppose we can write f this way. Here's the first thing we note. So note when n equals 0, the sine term goes away. So what I mean by that, so f of x just becomes a sub 0 times the cosine of just a sub 0, excuse me, because cosine of 0 is 1. And so we can start this at 1 instead. Okay, so again, we're being very generic here, so maybe I should stop being generic and be, hold on one second. Sorry, my house is crazy right now. I got people everywhere. They're packing up to go to the zoo. It's driving me nuts. Okay, so perhaps I say, let me reword this. I apologize because I think I'm coming about this the wrong way. I don't want to do that. I'm probably more confusing than anything. So let me go here. I don't want to. Have fun. I put it on the top of my car. Have fun. Sorry about that. So let's not say suppose f is equal to that. I guess we could, but I don't want to say it that way. All right, now I got to get my pen. Come on, pen. Come on. So let me start like this. Goal. Given f of x, some function, can we write it f of x as that in this form? So that's a better way of saying it. The way I was talking about it before, it seemed a little off, and I was also getting pulled apart because my house sounded like things were gonna go crazy. The struggles of doing teaching during the pandemic. So this is our goal. Given a student given a function. Holy heck, I'm having a rough day at it. Now, one of the things you learn, well, I guess we can attack that later, is okay. So, can we do that? So what we're going to do is assume we can. Now, here's an interesting thing to remember. Sines and cosines are periodic, correct? And you guys know that, say, from 0 to of period 2 pi. So we only need to consider, say, for example, negative pi less than or equal to x less than or equal to pi. So we'll just take nice symmetric intervals. What happens if we play around with this equation? So if I come over here, if I look at this equation, I can, since this is a sum, you know, if we assume this thing converges, you know, let's just pretend it does for now. We don't know. We're just going to pretend. And what we want to do is we want to say, okay, let's consider the sines and the cosine pieces similarly because it's a sum. So we know if the whole thing converges, then each piece would have to converge and vice versa. And so let's just pretend that that's all legal and that we can do it. And then let's multiply and play some games. So what do I mean by that? Well, what if I multiply both sides by, say, cosine of n theta, got calculus on my mind, nx, and I'm going to integrate. So let's look at that. On the left-hand side, I'm going to have f of x. And then I'll have cosine of nx. And I'm going to integrate that from negative pi to pi. And then on the right-hand side, I have, let's just look at the cosine. Well, we can just write it all out. So on the right-hand side, I'm going to have the integral of, so a sub n cosine of nx dx, and then of course this is plus the integral of b sub n sine of nx dx. Now, I am taking some liberties that most of you are probably unfamiliar with. Well, I shouldn't say unfamiliar. We're assuming, remember we learned in calculus that you just can't switch integrals and sums anytime you want if it's a series, unless you have this interval of convergence business. You remember all that stuff about power series? So let's just assume that what I did is legal. And if we assume that what I did is legal, you get this nice little thing that happens. Think about what you know about integration. What do you know about the integral of cosine? What do you know about the integral of sine on negative pi to pi?
I have a question.
Yes.
Like, did you multiply cosine nx on the right side?
No, I did not. That's important. Yeah, that's actually important. That would have been bad. So that, yeah. So this is going to be, okay, so let me also clarify something else. This is the unfortunate thing of me sometimes forgetting you guys are not, let's switch letters. So let's say, let's not do n, because I'm using n is my, so let's pick a k and multiply it by cosine of k sub x. So this is, so you're right. And that's my apologies. Because I always forget that you guys aren't as experienced as I am. So two things I did wrong here is this should be, let me clarify this. I did not put the cosines over here. So let's be very clear here. So on the right-hand side, you're right. You're going to have this series. So here, I'm just going to write it out in the cosine piece, and then we'll do the sine piece too. So you're going to have a sub n. Now you're going to have cosine of kx times cosine of nx, and this is very important because remember our sum is going from 0 to infinity. N is the index. K is fixed. So maybe K is 10, or maybe K is 300. And this is cosine here. Oh my Lord. So we'll just put right here plus the sine piece. But don't forget we're going to integrate this. So the integral, and then there's a dx here. Negative pi to pi. So what I want to do is I want to just look at what happens to this integral. We want to investigate this right here. And then we'll investigate the sine piece separately. So let's look at so all I want to look at right now is this piece. A sub n cosine of kx cosine of nx dx. Now this is a Calc 2 integral right here. Now remember, n and k are fixed. So what happens? We have two scenarios. We have the scenario where n and k are the same number. Case 1 is when n is equal to k. Okay. So when n is equal to k, what does the integral look like? It looks like a sub n negative pi to pi. When they're the same, let's write this as cosine squared of kx dx. And now let's remember, since cosine is an even function, cosine squared's even, so you can write this if you want it as 2a sub n integral from 0 to pi of cosine squared of kx dx. Now, how do you integrate this? This is, again, a Calc 2 integral. So you're going to write this as 2 sub a n, and then this is the integral 0 to pi. You pull out the 1/2, and then it's 1 plus the cosine of 2kx dx. So we're using that double angle formula. Okay, and then what happens now? Well, this is not difficult to integrate. So if we come up here, we're all over the place. This is a sub n, and then the first guy, you integrate 1, it becomes pi. And then if you integrate the cosine, well, what's the integral of cosine? It's sine. So this becomes plus 1/2 the sine of, when you plug in 0, it goes away, and then it's 2k pi. But we know what any integer multiple of pi is 0, so this goes away. So all you're left with is pi times a sub n. Actually, let me be more particular. This should really, since n and k are the same thing, I should write this as a sub, well, I guess it doesn't matter. Remember, we're assuming in this case that n and k are the same thing. Does anybody have a question about this?
How did you get rid of the sine 2k pi?
Okay, so what's the sine of 2 pi?
0.
0, right? What's the sine of 3 pi? 0. Sine of 4 pi, 0. Sine of 5 pi, 0. So k is an integer, right? So any integer multiple of pi is always 0. Does that make sense?
Okay, I got it.
Yep. So now let's hope we didn't make any errors, but if we didn't make any errors, then this is correct. Now, what happens? So this is what happens if n is equal to k. What if they're not equal? Well, if they're not equal, then we have to integrate it slightly different. There's a few ways you can do it. You can look up the integral on Desmos, or you can look up the correct way to do it is, well, not the correct way. The way you would do it in Calc 2 is you would use a trig identity. And maybe we'll put that as a homework problem for you to verify. But it's actually straightforward to do it as long as you have the correct trig identity. So let's go to the next page. So whether you look it up on, I don't know, whether you look it up on Desmos, or not Desmos, Wolfram, or you go in the back of your book, it doesn't matter what you do, but you should verify. So if n is not equal to k, the integral from negative pi to pi of sine, excuse me, not sine, of cosine kx times cosine of nx, this guy is always equal to 0. Always. You should work it out. It's tedious calculation, but it's one that is a Calc 2 integral. It's not hard to do. You can even do it in general, or if you want to get a feel for how it works, replace k and n with numbers. Pick any integers. It doesn't matter. 3 and 10, negative 6 and 5. Plug them in, do the integral. You'll get 0 every single time. Does anybody have a question about this? All right, so what does that mean? So that means the only term that survives, every k, for every single one of those terms in the sum, the only one that survived at all was this term, pi a sub k. Okay, so what about the sine piece? So now we have to do that, and then we'll summarize all this. So what was the sine piece? The sine piece was, we'll do case 1 here. Case 1 here, n equals k again. So remember, k is fixed. Now we're going to go through our sum. We're going to go n equals 0, then n equals 1, n equals 2. We're going to ignore all those. We're just going to stop. We're going to pick the one when n equals k. So when n equals k, what does the integral look like? Well, it's b sub n, negative pi to pi. Okay, now, what else do we have? Well, we had, if you remember, we have a cosine of kx, and then we'd have a sine of nx, but let's write that as the sine of kx dx. Okay, now, once again, this is a Calc 2 integral. And if you use a trig identity, you can work this integral out. But once again, it's going to equal 0. You should work it out. And by the way, if you want a real quick way of telling us it's 0, notice that the function, cosine is what kind of function? It's even. Sine is an odd function. So an even function and an odd function is an odd function. Look at the graph. You'll see the symmetry playing out. And if you integrate an odd function over a symmetric interval about the origin, the integral is always 0. So that's a shortcut way of seeing this. Another way of seeing this is just to do it out. So this is quite fascinating what we found, because it's going to be the same is going to be true for the case 2 that n is not equal to k. In that case, similarly, integral equals 0. So everything goes away except one thing. The only thing that stayed was pi times a sub k. That's it. Everything else is 0. So what does that mean? We have to write this down. So we conclude, remember the left-hand side was integral negative pi to pi of f of x cosine kx dx. What we found is that it's equal to a sub k times pi. So what does this mean? So you solve for a sub k, thus the only option for a sub k is a sub k, this coefficient must be defined as 1 over pi integral negative pi to pi of f of x cosine of kx dx. And this is for all k equals 0, 1, 2, etc. Does anybody have a question about this? Does anybody have a question? Okay, so I don't want to go through the calculation again, but we can do a very similar thing by multiplying both sides by the sine of some integer multiple of k. So in a similar manner, it's, I don't want to say easy, but so it is easy to show that the b sub k's has to be defined in an almost identical fashion. Now, what happens when k is 0, though, the sign of 0 is 0, so this thing goes away. So b of 0 is 0. Does anybody have a question or a comment? So again, think about how we started this, because we sort of said way back here, our goal is, given a function, can we write it like this? So what we did is we worked backwards. We said, assume we can. And then assume we can do these things like integrate term by term. So we said, assume in the ideal situation where it works. And we went through these calculations and we said, okay, if it is going to work, here's what these coefficients have to be. So So what do our calculations show? Our calculations show that if we can write as the above series, we must define A sub n and B sub n, or k, whatever letter you want to use. So these are called the Fourier coefficients of f. Okay. Here's some fun stuff for you too. So the series A sub n cosine of nx plus B sub n sine of nx. This series is called the Fourier series of f. Now, what's important to note is, I didn't say f is equal to it, because we don't know that. Just like when we studied power series and Taylor series in Calc 2, we didn't know that. We have to decide when a function is equal to its Taylor series. We have to decide what functions are equal to the Fourier series. Now, here's something that some of you are aware of, some of you may not be. It's also a convention to use Euler's equation. Euler's famous for lots of things. Remember, Euler's equation is e to the ix is equal to the cosine of x plus I sine of x. Now, Abdullah, you may not have seen that yet, but Jingzi and Zayshin, you definitely have seen this before. So this is called Euler's equation. And if you do some work with this, you can write your Fourier series. Instead of using sines and cosines, we can write it more compact. So what do I mean compactly? Well, we mean we can write the series as the sum negative infinity to infinity, c sub n e to the I n x. Where what is c sub n? Well, if you work out what c sub n means, c sub n equals 1 over 2 pi, the integral negative pi. So we could have done the same argument using exponentials instead. So we're saying is you can write Fourier series in trig functions, or you can write it in terms of the exponential function. So there's two ways to define a Fourier series. You can define it this way using exponentials, or you can define it this way using trig functions. They are equivalent. Does anybody have a question? Comments, concerns? Going once, going twice. All right, well then perhaps we'll stop there. I'm going to give you some problems to do, and then we'll move on Monday. And if you have any questions, please let me know. Has anybody seen Fourier series before? Maybe in a class?
Yes.
Yeah. Very good. All right. Do you guys have any questions?
Can I schedule an appointment with you on Friday if it's possible?
Friday. Yeah. Can you send me an email?
Sure, of course.
I got to look at my schedule, but most likely yes. I just don't know what time yet.
Oh, okay, awesome.
Oh, by the way, Abdullah, I figured out what you need to do. I got to send you an email, and I'll send you the link. It's all online now.
Oh, okay. Thank you.
Yes. Any other questions? All right, well, listen, Jingzi, send me an email. Abdullah, I will forward you an email. And thank you guys for joining. I will talk to you Monday, if not sooner. All right?
All right, talk to you later.
All right, take care, everybody. Be safe.
All right.